Hey, welcome again. Hey, more on the structure of the atom. This video is going to contain a lot of material. It's basically on the Bohr model, but we'll also be reminding you of how to calculate the frequency and wavelength of an electromagnetic wave, and also the energy of an electromagnetic wave. So some of this will be new, some of this will be a review from first year chem. Okay, Bohr model. All right, so let's think about the simplest atom there is. The hydrogen atom has one electron, and if we excite that hydrogen atom with a high voltage, and we look at the light, it would generate light. And then if we look at that light through a prism or through a spectroscope, you would see these four emission lines. So there's a red, like a turquoise, and then two violet lines. So again, if we excite the hydrogen atom, it gives off light, the atom gives off light. And if you break apart that light with a prism or a diffraction grating glass, you see these four emission lines, this red, turquoise, and two violet. So Neils Bohr, a Danish physicist, came up with the idea where these emission lines came from. Okay, so we want to talk about what he discovered. He won a Nobel Prize for this. All right, so here's a picture of a hydrogen atom, but instead of drawing circles for the energy levels, what I like to do is just make this vertical. So N is an abbreviation for the energy level, and so in the ground state, the hydrogen atom has an electron, on the first energy level in an s orbital. In the ground state, if it gets excited, it can go to other types of orbitals and other energy levels. So if we excite this hydrogen atom with high voltage, it's possible that this electron jumps up to the third energy level. Okay, so it gets further away from the nucleus, from that proton, so it has more energy than it did in the first energy level. And then what will happen is, it's attracted to this nucleus, it'll fall down. So if it falls down from 3 to 2, it would have to lose energy, and it loses energy in the form of light. And so this would give off, red light. So that explains that emission line. And it's a discrete amount of energy. This is the energy. This is the change in energy. You may not be able to see that, sorry. The change in energy from 3 to 2 corresponds to red light. Hey, so there's other possibilities. How about if this electron goes from 2 to 1? How about 2 to 1? Now notice that's a huge jump. It turns out that that's light that we can't see. So it's a little bit past the visible portion of the spectrum. And this is UV, ultraviolet. Every time an electron jumps to the first energy level, it's a type of ultraviolet light. Notice the different wavelengths here, much longer wavelengths, shorter wavelengths, okay? How about if we go back to exciting it? How about if we get this electron go to 4 and it goes to 2? So 4 to 2. So we said the red was 3 to 2. The turquoise is the 4 to 2. So let me see if I can make a turquoise line here. Excuse me. All right, let's make a turquoise line here. So now notice it's more energy. So of course, remember Roy G. Biv. Red light will have a long wavelength. Not as much long wavelength. Like that. By the way, let's define what a wavelength is. That's a wavelength right there. We use this Greek letter lambda. You remember? This violet light, I need violet, much more energy, shorter wavelength, okay? Let's get that. So this is a wavelength right here, like a sine curve. Whoops, sorry. So that wavelength is much shorter, has more energy. So UV is going to be over here. Now 4 to 2 is turquoise, so it's in here somewhere. Let's draw that turquoise line. A little shorter wavelength. Let me add a little green to that, just so it looks a little more turquoise-ish. All right, so what do you think, where are we at? 4 to 2. What do you think 5 to 2 would be? Yeah, that violet line. 6 to 2, violet line's right. So Niels Bohr came up with this idea and won a Nobel Prize. It's important to realize that these are discrete energies. And it tells you that the atom is quantized. It can only lose or gain certain amounts of energy. It just can't go from here to here. That's why we're not seeing a broad spectrum of light, just discrete emission lines. These are emission lines. Hey, how about this? How about 5 to 4? What would that be? That's a very small difference in energy. 5 to 4. So it's not a lot of energy. So think of Roy G. Biv. Where would we be? We would be over here. So yeah, infrared. Okay. Visible spectrum, infrared, violet. We have UV here. We'd have X-rays here, gamma. Over here we'd have some microwaves, then some radio waves. Okay, electromagnetic spectrum, electromagnetic waves. All right. Hey, let's do this. This won't be on the AP test, but I'll give you a couple problems to do. Some of you may remember this from first year chem. We can determine the wavelength of this red light using what's called the Rydberg equation. So I want to show you how this works. The Rydberg equation. Okay, it's 1 over wavelength equals some constant times 1 over the final energy level squared minus 1 over the initial energy level squared. And we can use this to figure out the wavelength. Okay, so let's use this to figure out what the wavelength of this red emission line would be, okay? So, 1 over wavelength equals, the constant's 1.0974 times 10 to the 7th, 1 over meter. So that gives you, you'll know your answer will be in meters, okay? And then it's 1 over, now let's think final. So this red light came from 3 to 2. 3 to 2, when the electron went from 3 to 2, it emitted red light. So the final energy level is 2. So we're going to square that. Minus the initial energy level is 3. 3 squared. All right, so 1 over lambda equals 1.0974 times 10 to the 7th. And then it's 0.25. 1 over 9 is 0.111111. So I already did this. So you get an answer, and then take the inverse, and the wavelength turns out to be 656 times 10 to the negative 7th meters. Okay? So you have a couple problems you could work on just for practice with that. Hey, one unit that's often used for in spectroscopy is the nanometer. So let's just convert this to nanometers real quickly. 656 times 10 to the negative 7th meters. And 1 nanometer nano is a billionth, is 1 times 10 to the negative 9th meters. And that'll give you then 656 nanometers. They're equivalent, just a different unit. Did I do that right? Let's see. 10, so when dividing by exponents, you subtract. So negative 7 minus negative 9 would be, so it'd be 2. So that's 10 to the second? Yeah. So 10 to the second, so 656. Hey, let me check my work. Hold on for a second. Yeah, I knew something was wrong here. Sorry about that. This is this. I'm glad I checked that. So 10 to the negative 7th divided by 10 to the negative 9th is 10 to the second. So it's 100 times that would be that. So sorry about that. That's the answer there. Okay? I did that work over on my desk and forgot what it was. All right. So let's then also introduce how to find the frequency of this emission line. So hopefully you remember C equals wavelength times frequency. C is the speed of light, wavelength, and we use this Greek letter nu for frequency. So we're going to determine the frequency of this light, the speed of light. We're going to use the speed of light. It's 3.00 times 10 to the 8th meters per second. We're going to divide that by the wavelength, 6.56 times 10 to the negative 7th meters. You notice the meters cancel out here, and we'll get 1 over second. Let me grab my calculator. All right, so 3 exponent 8 divided by 6.56 exponent negative 7 equals, okay, we'll use 3 sig figs here, 4.57 times 10 to the 14th. Now, it's either 1 over second or hertz. HC stands for hertz, 1 over second, a wave per second. So it's a tremendous amount of waves passing a certain point in a second. It's high frequency. That's the frequency of that red emission line. How about that? Huh? Okay, so I think we've used this before this year, but this is something you'll need to know. I'm not sure if the AP people want you to use 3.00 or 2.998 times 10 to the 8th. That'll be on the constant sheet. So I kind of think they're using 2.9998. I don't know why. Say you have 4 sig figs, I guess. Okay, energy. Energy. I hope you can see down here. You know what I might do? Let me erase. Let me do the energy portion up here, okay? Give me a second here. Let me erase this. I finally found a cleaner that's going to get this stuff off. I was having a hard time getting this off. Okay. These aren't the whiteboards that we had at school. Huh. All right, let's calculate the energy. So energy equals Planck's constant times frequency. So Planck's constant. So if you think about this, if you graph all the energies versus the frequencies, you'd get a straight line. They're directly proportional, and the slope of this, the slope of that line would be Planck's constant. You graph all the energies of electromagnetic waves, plot them versus energy. They're directly proportional. So we could say mathematically, you can say energy is directly proportional to frequency, but that's no fun. So we have a proportionality constant, just like pi, just like a lot of, like R. So that's Planck's constant. So we can calculate the energy of this red emission line. Planck's constant 6.626 times 10 to the negative 34th, and it's a joule times a second. And then we're going to multiply it by this, by frequency, 4.57 times 10 to the 14th. And I'm going to put 1 over second here.